a lot of mathematicians are driven by the pursuit of beauty. And I think many of us have a little bit of an artist heart, and we look for pretty things, and we really find them in mathematics. And it's kind of amazing how when you look for pretty things, you find incredible mathematical structure. We study these objects, and all of a sudden we find these very beautiful, intricate structures that fit together really tightly sometimes. And you just look at that and you know that that just cannot be an accident. And there must be something that I need to understand underneath. Let's say that you are in the plane and you draw some number of lines. Okay? And you can draw them in any way you want, but you want to draw them in general position, meaning that no two of them should be parallel and no three of them should pass through the same point. So I cannot pass it through here, but I can pass it maybe like this and so on. So I have n lines. Are you able to count what is the number of regions that you form? 1, 2, 3, 4, 5, 6, 7, and so on. It turns out that for this problem, the number of lines, so the number of regions is 1/2 times n squared plus n plus 2. Okay. What happens if you take a cube of cheese and now you make n cuts through it? You could say a little bit less poetically, you're in three-dimensional space and you are going to draw n planes. So here's one plane, and then here's another plane, and then you draw another one, and so on. And it turns out that if you have those conditions, then again the number of regions that you form does not depend on where you drew the planes. And it's equal to this formula. 1/6 times n cubed plus 5n plus 6. Okay. If you're just interested in problem solving, you might think that this is the end of the story, but you could say, okay, what about the fourth dimension? What about the first dimension? So like if I have a line and n points, how many regions do I get? I get +1. So far, this doesn't tell me anything. It's kind of cute, and maybe I can imagine that I can keep doing it. But somehow what changed this for me was realizing a pattern here, which is that this number is n choose 2 plus n choose 1 plus n choose 0. This number is n choose 3 plus n choose 2 plus n choose 1 plus n choose 0. And this number is n choose 1 plus n choose 0. In this formula, when I write this symbol, I called it n choose 2. And this is the number of ways of choosing 2 out of n objects. When I write n choose 3, that means I have n objects in front of me and I choose 3 of them. What is the number of ways of doing that? And this goes on in every other dimension. And this was my introduction to what is now known as the theory of hyperplane arrangements. The first thing that you can imagine is that if you ask the same question in d dimensions, you can probably guess what the formula is for the number of regions in d dimensions. The way that we have set up schooling for very large groups of people is that we split knowledge into different pockets. And I don't think we emphasize enough how these pockets are often the same pocket, and we're really talking about many of the same things from different points of view. So you take an algebra class, you take a geometry class, you take a combinatorics class. The more that you learn mathematics and the deeper that you go into it, you really start seeing these really beautiful interconnections. I definitely am very interested in the way that combinatorics talks to geometry, the way that combinatorics talks to algebra. Sometimes I'll just meet people in a different field that have these pictures that just look very familiar to me. And I know that if I talk to this person and if we are able to find a common language, we're going to find some beautiful things together that probably they couldn't do on their own and I couldn't do on my own, because we really need to talk to each other.